what are the structure of electrons in atoms, what are atoms composed of, some of the properties of atoms. Now we're going to talk about how do these atoms come together to form molecules and compounds, right? And there's going to be different types of ways they can bond together, and then the type of bonding will tell us about the properties of the material and also the shape and even more properties based off of things like shape. All right, so first thing we learn about bonding is something called the octet rule. And so these elements, except noble gases, so noble gases are very stable, right? So noble gases are stable because they have a full valence shell, meaning a full S and P. What's that? Let me take a look. They're really stable, so what that means is we call them inert, right? They have a full valence shell. They're inert, which means they're very unreactive, and they're very unreactive because they have a full valence shell. So remember we were talking about the anomalies and the periodic trends. They had half-filled p orbitals or unfilled p orbital and a full s shell, right? Those ideas are the same thing that apply to reactivity of noble gases. They're very inert because they have a full valence shell, which means they don't like to react. They're very happy with the full valence shell. So these energy levels and stuff, they ultimately they tell us about how these atoms are going to react with one another. And so compounds, right, which are going to be a mixture of different elements, these are the result of the formation of chemical bonds between two or more different elements, right? So molecules can be as simple as two atoms of the same type or two atoms of different types, and they can be as complicated as something like a strand of DNA that can have millions and millions of atoms within a single molecule, right? So the extent to matter that's from molecules is pretty vast. In stars in the solar system, a lot of times we just have elements. Once we get up to something like Earth or other planets, then you start to form a lot of these molecules. And so in the formation of a chemical bond, the general trend of things, right, is to gain or share valence electrons to complete their outer shell and to basically attain a noble gas configuration, right? So you think is like the noble gas is like the state of enlightenment for an atom or a molecule. Why? Because that's the most stable conformation. So how things react is usually to move towards something that looks like a noble gas. And so the tendency, right, a noble gas, we'll always say, also has a full valence shell, which means it has 8 electrons in its valence shell. How does that relate to the valence shells we were talking about before in electron configurations, right? If we have an S with 2 electrons and a P with 6 electrons, 2 plus 6 equals 8. We have 8 electrons total for a noble gas. Right, so that's why there's 8 electrons in a full valence shell. And if you look at the periodic table like we have over there, you see that for each of them except helium, helium's a special case because it only has 2 electrons total. But all the other noble gases are in group 8, which means that they have a full S shell, and a full P shell for that principal energy level. So all of them have a full valence. And this is what allows them to be inert and very unreactive. They're very stable in this state. And so the tendency of atoms to have 8 electrons in their outer shell is known as the octet rule. And so this is a general rule that tells us how things are going to bond, either ionically or covalently. Okay. And so first, we talked a little bit about this earlier, but how does an ion form, right? An ion is a charged particle. And it can be produced when an atom loses or gains one or more electrons, right? And so here we have a sodium atom, we see that we lose the electron in its outermost shell. So maybe this gets hit with some light, right? And that knocks the electron off of the atom. The resulting structure, or the resulting charge, is that we have now 2 plus 10, we have 10 electrons total. We have 11 protons, which means we have 1 extra positive charge compared to our negative charges, right? So now we have a positively charged atom, right? Removing an electron makes it positively charged. And this specific type of ion is called a cation, right? So a positively charged ion, it can be a molecule or an atom, right? So this can be a molecule or an atom. So ion doesn't have to be just a single atom, it can also be a molecule. And a cation is just one that's positively charged. And so it can be ionized a couple different ways. One of the ways we talked about is, if you hit it with energy from light or something, that can knock off an electron and ionize that atom. And all you have left now, right, is a full valence, right? So you see that when we got rid of that 1 extra electron, now the outermost shell has 8 electrons in it, right? So now it has a noble gas configuration. So that tendency says that this element, when it forms bonds, is most likely going to lose an electron in these processes. Why? Because that's the easiest way for it to reach a noble gas configuration.
But it won't always necessarily stay that way?
Say that again?
It won't always necessarily stay that way?
With a noble gas configuration?
Yeah.
Yeah, so if you have metallic sodium, in this case, right, it can form a series of bonds where it isn't like that. Sodium is almost always found as sodium plus, right? So it is actually mostly found, if it's on its own in an elemental form, it'll be in a positive charged state. Why? Because it's actually so easy for it to lose an electron. Why is it so easy for sodium to lose an electron? Well, it's very metallic. You can tell by where it is on the periodic table. And also because it only has to lose 1 electron to become a noble gas type configuration, right? So what would be the closest noble gas to sodium? Yep, neon, right? And so that configuration where you have 2 electrons in the 1s shell, 8 electrons in the n equals 2 shell, that's going to be the neon noble gas configuration. And that's what sodium wants to be like. It's going to be very stable in that state. However, if it's not surrounded by something like water, we'll talk more about this, that positive charge just existing on its own is not very happy in general. It has to be next to something that'll help balance that charge too. An anion is an ion that's formed when a neutral atom gains an electron, right? Because electrons carry a negative charge. Electrons carry a negative charge, and so when we gain an electron, we gain a negative charge, right? So, and that's how we form an anion, which is a negatively charged ion, right? So this is a negatively charged ion. And I'll go back and forth between this slide and the previous one in a second, because one other thing I want to mention is the process of gaining an electron. It's called reduction. And sorry, I'll try not to write down there as much. But this process is called reduction. So we're gaining an electron, but we're reducing the charge, right? We're making it more negative, which is why the process is called reduction. In a second, I'll go back to the other slide and I'll mention, when we lose an electron, that process is called oxidation. Right, so on this one, the process of, I'll do it up here, of losing an electron is called oxidation. Right, so this process of losing an electron is called oxidation. And this will make not necessarily more sense, but in the the olden days, they looked at a lot of reactions and how oxygen moved around between atoms, and when you gain oxygen, you lose electrons. It's kind of the trend that they found. So that's why it's called oxidation. And when an ion is charged, or an element or a molecule is charged, the specific charge of that element or molecule is called the oxidation state. Right? So I'm just trying to familiarize you guys with this verbiage that we're going to be seeing and using a lot, right? So it's a little bit opposite trend in our head. Reduction is gaining an electron, right? Because we're reducing the charge. Oxidation is losing an electron. And so the ionic charge of an ion is dependent on the number of electrons lost or gained to reach what kind of configuration you think? Right, what type of electron configuration do you think would make our elements and molecules most happy? The noble gas configuration, right? So the noble, again, you keep seeing noble gas configuration popping up here. And so this chart might look a little confusing at first, but what this is these are the group numbers from the periodic table, right? So if we look at lithium, sodium, potassium, rubidium, those are all going to be group 1 elements on our periodic table, right? And all this chart is stating, and what you guys can familiarize yourself with, is what's the easiest way for these elements to reach a noble gas, right? If it's lithium, well, it's easier for it to lose 1 electron than it is for it to gain 7 electrons, right? So that tells us what is the most preferred oxidation state or charge that this element will have, right? So lithium, sodium, potassium, rubidium, and cesium, those are all going to be most likely to just lose 1 electron. So their oxidation state or their preferred charge when they lose an electron is going to be +1, right? So this is the +1 group. I'm going to write them up here in red. So this is +1. Magnesium is 1 group over. So to reach the noble gas, they need to lose 2 electrons, right? So they become +2 because they lose 2 electrons to get the same noble gas configuration that it took sodium or lithium to only lose 1 electron. So these are going to be the +2 oxidation states. And then there's group 3, and where group 3 is kind of where weird stuff starts to happen. Group 3 and group 4 are a little odd. The only one that has a +3 oxidation state is going to be aluminum, right? If I were you, I would just put that group 3 as +3, right? Because if we think about it, if we have 1, 2, 3, 4, 5, 6, 7 in between 8, right? 3 is still going to be easier to lose electrons, whereas 5 through 7, it's going to be easier for them to gain electrons. And we can think about this just in terms of numbers, right? If you're in group 3, it's going to be easier for you to lose 3 than to gain 5 to reach the noble gas. And when I say to reach the noble gas, that's the closest noble gas to that element, right? When we're doing electron configurations, it was the most recent noble gas that we're looking at. Here, it can actually be the noble gas that's ahead of that element, right? So fluorine, for example, is in group 7, right? It's going to be easy for it to gain 1 electron to become like neon rather than lose 7 electrons and become like helium, right? So that's how we're thinking about, there's 2 noble gases that you're in between. Which one are you more likely to move towards? The one you're closer to. It's going to be easier for you to do that. So once you get to group 4, that's exactly in the middle, right? So these have no preferred charge. Right? So carbon, silicon, what else is there? Germanium. Those ones aren't going to have any preferred charge because they're exactly 4, right? They're not likely to either gain or lose electrons to become to have an oxidation state. Once you get to 5, though, now you've kind of crossed the halfway point. At this point, it becomes easier for you to start gaining electrons to reach a noble gas than losing electrons.
So will they never really be noble?
Yeah, they're never actually noble gases, right? Because they don't have the same number of protons as noble gases. But in terms of the electronic structure, the full valence shell, that's what they're trying to reach. Remember, you can have different number of electrons, different number of neutrons, but the protons always give you the identity of the element. So you can have, each of fluorine, chlorine, bromine, and, you can have iodine, barium, and cesium. They can all have the noble gas configuration of xenon, for example. But they're all still different elements because they have different number of protons in each of them. All right, and so once we cross over group 4 into group 5, now it'll be easier for nitrogen, for example, to gain 3 electrons, which means we have a -3 charge, than it will be for it to lose 5 electrons. And then for oxygen, sulfur, it'll be easier for them to gain 2 electrons, and all the halogens, fluorine, chlorine, bromine, it's easy for them to just gain 1 electron to then become the noble gases. And so why is this useful? Well, this is going to be useful for determining molecular formulas for ionic compounds, because it's going to tell us how to balance the charges in these elements. But this is how we get ionic charges, by looking at the periodic table. Is it easier for us to lose or gain electrons to become a noble gas? In general, what you'll see is that all of the elements in blue on the left-hand side of this chart, those are all going to be metals. And metals tend to lose electrons. They like to oxidize. They like to lose electrons and become like a noble gas. All of the non-metals, like the main group elements, those tend to form negative charges. They tend to form anions because it's easier for them to gain electrons. And those tend to be the more electronegative elements, the higher ionization energy elements. So they're going to pull electrons more strongly. Sam?
So the elements in group 4 just be neutral?
The elements in group 4, yeah, those are pretty much going to be neutral all the time. And those are the ones that can bond the most ways with the most different elements, right? Which is why carbon is such a prevalent atom in biological molecules. Why? Because it can bond to a lot of different elements in a lot of different ways. It allows it to have unique shapes and a non-rigid structure, and it's very mobile in that sense. And that's why, if you have sci-fi, they say, well, there's carbon-based life. Is there silicon-based life? Why? Because silicon is right under carbon on the periodic table, which means it has similar valence structure, which means it should have similar bonding properties. And it does in a lot of ways. Silicon has a lot of similar bonding properties as carbon. Right? So these compounds, this is how they form their ionic charges. They can be broken up into two different categories. We can have ionic compounds, which are electrostatic bonds. Bonds between ions. Ions, that's what an ionic compound is going to be. And then molecular compounds, these are, I don't really like the word molecular, but these are going to be covalent compounds. And these are going to be a sharing of electrons. Right, so for the purpose of this class, this is why we don't worry about any D block or F block bonding, right? This is just mostly dealing with the s and p orbitals of all of these atoms, right? These covalent compounds and ionic compounds. And the ionic compounds are going to be made of cations with a positive charge, electrostatically bonding to something with a negative charge. And how does that happen? Well, we're going to transfer electrons from one atom to the other. And so these different type of bond affect, again, the same way the structure of the electrons within an element affect its properties. The type of bonding that we have affects the properties of the compound as well, right? So the type of chemical bond is responsible for many physical and chemical properties, right? So ionic compounds tend to have high boiling points or melting points. They tend to be solid materials. where covalent compounds tend to have low melting points. And they can be any state of matter. Whether something is conductive or not is also dependent on the bonding structure of the material itself. So for example, if you have, Vanessa?
Sorry, what is that second word after solid?
Solid materials.
Oh.
So for example, if you take something like sodium chloride and you put it in water, it has ionic bonds that becomes very soluble in water. The salt will dissolve, and you know that when you put salt in water, it'll dissolve. But because you have ions that form that compound, now that water becomes conductive and you can complete a circuit with it, right? So if you stick a light bulb with two, anodes and cathodes sticking into it and plug it in, the salt water will conduct electricity and plain water will not. Or if it's a covalent molecule like sugar, you put sugar in there, so sugar also dissolves in water, but it's not an ion, so that won't conduct electricity, right? So the structure of these bonds gives a lot of properties to the material. Ionic compounds tend to be very soluble in water because water molecules can stabilize those charges pretty easy. Right, so how does an ionic compound form? Well, we have two elements, one that's going to form a cation and one that's going to form an anion. And electrons are going to be transferred directly between two atoms. So they means one gains, one gets reduced, and then one gets oxidized. So here we have a chlorine atom and a sodium atom that are interacting with. They're right next to each other. We know that sodium is losing one electron. Write this a little better. Losing one electron away from noble gas configuration. And then chlorine is one electron away, gaining one electron away. Away from a noble gas configuration. Right? Because if we gain one more, we fill our octet on the chlorine, and if we lose one on the sodium, we gain a full octet, or we gain a full valence shell, right? So what happens is when these two elements come next to each other, this electron will be transferred completely to the chlorine atom. And what you have as a result is you have a positive charge here and a negative charge here. It now Summer?
So sodium is being oxidized?
Yeah, so this one gets oxidized,
And the other one is getting...
reduced. Yeah. Mhm.
It makes sense.
You just asking if it's oxidized or reduced? Yeah. Yeah, oxidized. Sodium is getting oxidized and chlorine is getting reduced here. And so now that you have two positive and negative charge right next to each other, they will interact the same way that a positive and a negative charge interact anywhere else in the world. They are attracted to each other, so they form what's called an ionic bond, right? So this forms an ionic bond between these two. Okay. Mm-hmm. There's definitely still an attraction there, and that's exactly where this ends up, is that if you have an uneven, one's going to be oxidation state of +2. That means if you have atoms that only form an oxidation state of -1 for the anion, you need 2 of them to balance the charge. And that's actually how the ionic compound is going to form. That's how you can predict how it forms, is that based off of balancing the charges, that tells you what the chemical formula is going to be. But yeah, so that in a little bit we'll talk about exactly that, because that's actually the most important thing when you're determining ionic compounds, chemical formulas, is can I identify how the charges are supposed to balance out with each other, and that's what the dry lab for today is supposed to be. Good question. And so just to reiterate, atoms that gain electrons are going to be the nonmetals to form negative ions, which are called anions, and atoms that lose electrons, which are going to be metals in general, form positive ions, right? And then these two interact through electrostatics, right? They just interact for like a positive and a negative charge. And so from these preferred oxidation states, you can form or predict what the chemical formula is going to be. And what you want to keep in mind is that the net charge is equal to 0, right? So the chemical formula is just going to be the elements in a molecular compound, with the amounts indicated by subscripts. Right, so the molecular formula is just a map to tell you what does that molecule look like. Based off the molecular formula, or not exactly what the molecule looks like, right? For simple molecules, you'll be able to do that. For complicated molecules, it's a little tougher. Right, so for ionic or covalent, so this is for both ionic and covalent compounds. Right, the molecular formula indicates how many of each atom you have in a molecule. And how do you know? The symbol. Tiffany? Yeah, of course. Alright, so like what Kai asked, he says, well, what happens if you don't have an even number of charges in your, in your ionic compound, right? So if you have a sodium and then let's say you have oxygen, how does that affect the molecule? Well, it tells you that you're going to need a different number of each element to then neutralize the total charge for that compound. And how do you, did I give you enough time? Okay. So how do you know when you had enough of each element? Well, you have a net charge of 0, right? And what that means is that if you add all the negative and all the positive charge, it equals 0. Right, so if we look at our example here of sodium chloride, we have a +1 charge on the sodium and a -1 charge on the chlorine. Right, so when you add those together, what do you get? 0, right? Which means that this molecule is good. Right, we've satisfied that charge is neutral. And that's because in general, you don't like just to have charges floating around, right? That's pretty unhappy, which is why stuff that's charged or that gets ionized tends to be very reactive, because it's trying to get rid of that charge or balance it somehow. So you want the net charge to be 0, and also in the chemical formula, you're also going to want the lowest possible whole numbers, right? So I'll just put a little star here. the lowest possible unit. And what I mean by that is, for example, the chemical formula for sodium chloride is going to be NaCl, right? The fact that these two elements are right next to each other indicates that they're bonded to each other and they form a molecule. We have one element, our metal, sodium, and then the other element, chlorine, our anion there. Together they form sodium chloride. And how do we know that it's NaCl instead of Na2Cl2, right? That would still have a total net charge of 0 because you would have +2 here and -2 there. Well, you want to make sure that you have the lowest possible unit, right? Which means that the lowest whole number of each of them to balance the charge. What does that mean? Well, you can divide both of those subscripts by 2. So you divide it by, if you guys remember from previous courses in math classes, the lowest common denominator, right? If you divide them both by the largest common factor, divide them both by that, and it gives you the whole numbers. That'll give you the simplest unit for the molecule, right? And in our chemical formulas, we usually don't write the number 1 for subscripts. Sam?
So you should always try to simplify it.
You always want to simplify it to the simplest unit, right? So sodium chloride technically could have a subscript of 100 under both of them, which makes sense because the total charge is 0. But we want to have the simplest possible unit, the simplest molecule possible for a given two elements. Right, so when we're building our ionic compounds, we use a chemical formula to represent the molecule. And we want to make sure that we have a net charge of 0. That's how we're going to balance out the amount of each ion, and then we're going to have the simplest possible unit. And so, leading directly into what Kai's question was, which was, well, what happens if you have an uneven number of charges between anions and cations, right? We use subscripts to indicate how those electrons are going to be transferred, right? So subscripts indicate the amount of each element in the molecular compound, and it tells us actually the amount of each element in that molecule, and that's given to us technically by the charges on our cations, right? So if we looked at our periodic table, we see magnesium is in group 2, which means it prefers a +2 charge. Chlorine is in group 7, which means it prefers a -1 charge, right? That means if we have +2 and -1, we need 2 of the -1s to balance out the charge, right? So what happens is the magnesium atom will transfer 1 electron to 1 chlorine and another electron to another chlorine. Now we have a -1 charge on this chlorine here, a -1 charge on this chlorine here, and a +2 on the magnesium. But if we added up all of the charges in the circle I just drew, what's the total charge going to be?
0.
Yep, we have 2 plus -1 plus -1, which equals 0. So our total net charge is equal to 0. So this is going to be the simplest molecule unit of this compound. And then the chemical formula would be MgCl2. Why? Because we have 2 chlorines and we only have 1 magnesium. All right, so that would be the chemical formula for this ionic compound. Right, and the important thing to remember here is that the charges give the subscripts or the ratios, right? And that's what that table was telling us. What are the preferred charges on the cations and the anions? Am I good to go on to the next one? All right. And so once you have the molecular formula, then we have to know how to identify these molecules. So the next portion of the class is kind of, or the next lecture and a half or so is dedicated to naming of these different ionic compounds. There's going to be two different types. There's going to be type 1 and type 2 ions, right? So the type 2 are in blue, and type 1 are in red, right? So that's going to be group 1. The type 1, you know the charge just based off of what group it's in, right? So anything in group 5 is going to be -3, anything in group 6, -2, anything in group 7 is going to be -1. What distinguishes between type 1 and type 2 is that, again, we're looking at now the funny transition metals, right? And the transition metals can have multiple charges, potentially, right? So these can have, I'll put it in blue since it's in blue. These can have multiple charges, or we can say oxidation states. Right, so for example, iron can be iron 2 or it can be iron 3. Right, and that means that it's either positive 2 or positive 3 within any given compound. And what we're going to find out is that the charge on the type 2 ionic compounds is just going to be dependent on the molecular formula, or if you're given the charge, you can then determine the molecular formula based off of that charge itself. Type 1 is going to be relatively straightforward because you just have to get the appropriate ratio that we talked about on the previous page. Right, and so these are going to be, in general, transition metals and other heavy elements that have like D or F orbitals. And so these type 1 can usually fall into a category of binary ionic compounds. They usually only contain 2 elements, and they can be a different number of those elements. And so type 1 ions are just going to be any type of ion that forms only one ion, right? So sodium is a type 1 ion, it only forms a +1 ion. And so in these compounds, the charges of the cations must equal the charges of the anions. The net charge, because it has to be equal to 0, right? Ultimately, everything's trying to reach that neutral state. Then neutral state means that everyone has their octet satisfied. They have a noble gas type configuration. And the subscripts, again, are going to be used to balance the charges between cations and anions. And we'll find that when we have type 1 or type 2, we have 2 different naming conventions for each of those, though they're relatively similar in most ways. Type 2, you can imagine, you just have to specify what the charge is. And so here we have 2 examples, right? We'll talk about where these names specifically come from. We have sodium bromide, right? So sodium is Na, and what charge does sodium like to have? Does anyone remember? It's in group 1, right? Which means it wants to be +1, right? So this is going to be plus, and bromine is in group what? It's atomic number 35, right? And what group is it? Right? That's the group number 7, right? Which means that it likes to be what? Minus 1, right? It likes to be minus 1 because it only needs to gain 1 electron to become the noble gas. And what's right next to bromine? I can't see. Is it krypton?
Yeah.
Yeah, the noble gas krypton. You gain 1 electron, it becomes like noble gas krypton. So it likes to be Br minus like that, right? We don't write 1s in chemistry for whatever reason. We usually omit them, and that'll be a common trend with most 1s in the class. Right, so we have a +1 and a -1, which means the chemical formula for this should be what? Right, how would we write the chemical formula for this compound? NaBr, right? We don't need any subscripts because we don't write 1s, but we only need 1 of each element to get the net charge to equal 0. What about potassium? What's the charge on potassium? +1. Right, so this is going to be K +1. Sulfur, or sulfide, is going to be the anion name for sulfur. And what's the preferred charge on sulfur? -2, right? So this is going to be S2 minus. So when we write the charge for something, we usually put the number in front of whatever the sign is. That's just a standard convention. Right, so that means that we need how many potassiums to get a net neutral charge of 0? 2, right? So then what should the chemical formula for this be? K2, because that tells us that we have 2 potassiums. And we have 1 S, right? Because 1 sulfur atom has a -2 charge. We need 2 potassiums to neutralize the charge of 1 sulfur. Right, so these would be our 2 chemical formulas for each of these compounds. What about calcium chloride? What's the preferred charge on calcium? Right, calcium should be Ca2+, and chlorine is in group 7, so it should be what? -1, right? So Cl minus, which means what should our chemical formula be here? CaCl2, right? We need 2 -1 charges to neutralize the +1 charge of calcium. And then sodium, you said was +1, sulfur was 2-, so what should the chemical formula for that be as well? Na2S. So those would be the molecular formulas for calcium chloride and sodium sulfide. So notice that if you're just given this name, you already automatically know what the chemical formula is just based off of what these charges should be on these atoms, right? That tells you, based off the oxidation state, which is what's most likely to reach a noble gas electronic configuration, which we know is a very stable configuration, which is what we spent the last week talking about. That tells me how this is going to bond in a molecule in the most favorable way, or in the happiest way, right? And for different molecules, sometimes you need more anions to compensate for the charge, and sometimes you need more cations to compensate for the charge. It really just depends on which one has the larger value of the charge, the anion or the cation. The cation was which one, the positive or the negative charge? Positive, right? So if you like cats, you can remember that cats make you happy, and that's why they're positive. If you don't like cats, I don't know what to tell you. So this is one of the big parts of ionic compounds, is determining the chemical formula from the name. And the other way is, how are we going to name these compounds, right? So right now these names, they don't mean much because we haven't talked about it. How do we name these compounds? So when we're naming an ionic compound, we always name the cation first. All right, so the cation is the positively charged, the positive ion, right? Or we can also say the metal, usually the metal goes first. And the anion last. So this is going to be the negative ion and non-metal. The cation is simple, it's just the name of whatever the element is, right? So for example, Na, we just put sodium. We don't modify the name at all. Potassium, we just put potassium. There's no modification. However, for the anion, the name takes the root of the nonmetal, or the anion element, and we replace the ending with "ide," right? So if we think about a couple anions, let's think about nitrogen. We can think of chlorine, right? These are the original atoms' names. We're going to convert them into the anion form, right? So nitrogen is neutral here, chlorine is neutral here, and we'll do oxygen as well. Right, so what do you guys think? Well, first of all, what's going to be the charge on nitrogen? What's the oxidation state of nitrogen? -3, right? Because it's 3 electrons away from becoming a noble gas. So it's going to be N3 minus. And what do you guys think the name becomes? Nitride. Right, so we replace the ending with IDE, becomes nitride. What about chlorine? What does the charge on chlorine become? What's its oxidation state? -1, right? So it becomes Cl minus. And what do you guys think the name becomes? Chloride, right? So chlorine and the halogens are a little easier, so that becomes chloride. And what about oxygen? What's the charge on oxygen? -2, because it's 2 electrons away from becoming like a noble gas. This becomes 2 minus. And what do you guys think the name will be? Oxide, right? So it becomes oxygen goes to oxide. All right, so you'll get more familiar with these the more practice you get. And sometimes you can kind of just sound them out, right? Sulfur becomes sulfide. It's not as easy as chlorine or bromine, or all those end with ene. What else we have? Chlorine, bromine, fluorine. All those become fluoride, chloride, bromide. Those are pretty easy. Oxygen, nitrogen, those are a little, you kind of just get used to them the more you do them. All right, so that's how we name type 1 compounds. All right, so notice that when we're naming it, we don't specify the number in the name. Right, and this is only true for ionic compounds. For ionic compounds, specify the number of elements in the name. And we'll find that once we get to covalent compounds on Wednesday that we do specify the number in the name. And the reason for that is why do you guys think we don't have to specify the number of elements in the name here? How do we know how many of each ion to have? The subscript tells us the number, right, that we each have. But how do we know what the subscript is supposed to be? Electron configuration, which gave us, what electron configuration are we trying to reach? The noble gas, right? So we want to reach the noble gas. And what do we become when we reach the noble gas? Are we still a neutral atom? Right? If we're chlorine and we gain an electron, are we neutral anymore? No, now we're an ion, right? So the reason for ionic compounds, we don't have to specify the number in the name, is because the charges tell us the ratio, right? The charges themselves tell us how many of each we need to make the net charge equal to 0. Once we get to covalent compounds, that's not going to be the case anymore. Right. Okay, so for these, what would we name this first element? What do you guys think? right? Magnesium chloride, because magnesium, the metal, always goes first, so we have magnesium, and then the anion is chloride, right? We replace the ending of chlorine with chloride. Let me write that a little bit better. Chloride. We put the metal first, and then we have the anion plus ide. What about the next element? Sodium iodide. Right? I is iodine. We replace iodine, or iodine becomes iodide. And what about the last one? Aluminum fluoride. Oops, sorry. Right, so that's what the ionic naming practice is going to be for the dry lab today. Is you go back and forth between the two. And what's the important thing to keep in mind? Net charge is equal to 0. In the naming convention, well, we get the number of each just because we know what the charges have to be on these ions. How do we know? Well, we look at the periodic table. How do they become noble gases to become, very stable like those? Do they lose or do they gain electrons, and how many do they gain? So the last thing I'm going to mention before I kind of let you guys loose to work on that, and there's plenty of examples in the lecture notes, so we're not going to go over all of them. This isn't going to be on the quiz, by the way, on Wednesday. This will be on the next exam, but not on the quiz. Is how do we name the type 2 ions, right? So these are cations, and they're only going to be cations that are type 2 that form more than one ion, or they have, we would say, multiple oxidation states. Right, so these metals can have multiple charges just depending on the environment that it's in. It'll be +2 or +1 or +3, just depends. And so the only thing that changes for the naming convention for these is that the ionic charge is included as Roman numerals in parentheses in the name. So if you don't remember your Roman numerals, the good news is manganese is the highest possible charge on any element, and that only goes up to +7. So we just have to remember to maximum of what the 7 Roman numerals is, right? Like 1, that's 1, 2, 3, 4, 5, 6, and 6 and 7, right? So those are our Roman numerals. 1, 2, 3, 4, 5, 6, 7. And so since this is only for cations, that means that if you have a Roman numeral 2, you have iron 2, for example, it would look something like iron 2, chloride. What would the molecular formula be for this compound? What's the charge on iron here? 2, right? So this means it's Fe2+. We know that because it tells us, right? That you can have multiple oxidation states, so it has to specify that. What about chlorine? What's the -1, right? It would be FeCl2 because we need 2 chlorines to balance out the charge on the positively charged iron. Okay. Well, that was the example. That was the next one. Let's go here. So we have copper right here, and we have 2 different copper compounds. they're both with oxygen, right? And this tells you that depending on which compound it is, the copper has a different oxidation state, right? Because it's different ratios of copper and oxygen, right? So what is oxygen? The state for oxygen always. It's not a type 2. It only has one oxidation state. What should it be? It should be 2 minus, right? So oxygen is 2 minus when it forms an ionic compound. So in both of these cases, it's 2 minus there, right? Which means that to determine the charge on copper, we see, okay, how many coppers are there to neutralize that charge? The subscript tells us how many coppers we need, right? So for the first compound, we have how many copper atoms in this molecule? 2, which means that each copper has to have a charge of what? Plus 1, right? So you need 2 copper plus 1s, right? Because we have 2 times plus 1 plus negative 2 equals 0. That's what gives us our neutralization of the charge. If we think about it, the actual compound, we have copper plus 1, copper plus 1, right? And we have an oxygen 2 minus. We're just trying to determine how many little copper plus 1s do we have there. What does that charge have to be such that everything that I've circled there, the total charge is equal to 0. So everything in my little sphere there has to be a net charge of 0. And the only way that that's true is if it's plus 1 for each copper there. Right? And because it's a type 2 cation, how would we name this compound? What goes first when we're naming ionic compounds? The cation, right? So the positive charge. So copper goes first. So we have copper. And then what do we have to consider because it's type 2? The charge, right? And the charge on it is what? 1, which means that in parentheses we put a Roman numeral 1. And then everything that's different between type 1 and type 2 is over. What's the anion here? Oxygen. It becomes what? Oxide. So this is copper 1 oxide. What about for this second compound, right? So this is going to be a different oxidation state for copper. We know that there's 1 copper atom and 1 oxygen. What does the charge on this copper have to be so that everything in that circle is neutral? Plus 2, right? Because we only have 1 copper atom and it made the compound neutral. How do I know it's neutral? Because they gave me the chemical formula. When you're given the chemical formula, that tells you what the charge has to be based off the ratios, right? 2 plus 2 plus negative 2 equals 0. So then we start by naming our metal first. We have copper, and what goes in parentheses? Roman numeral 2. And then we have an anion again, so that becomes oxide. So because the molecular formula tells us, or the chemical formula tells us we only have 1 copper, that's what tells us that that has to be plus 2 to neutralize the total charge. The first one said we have 2 coppers, which means that to neutralize the total charge, we needed 2 of whatever that charge on that copper was. Since they're only whole number charges, that could only be a plus 1 on each of the copper atoms. All right, how do we feel about the naming and getting chemical formulas for ionic compounds? Thumbs up, side. All right, we'll practice with it with the dry lab today. All right, so the only thing you might see on the lab is that we have potentially what are called polyatomic ions, right? So remember I said both elements and molecules can be charged. If you see something like this or one of the names like this, the only thing you treat differently for the polyatomic ions is that is a covalent molecule that has a total charge on it, right? So if we look at nitrate, right, that means that you treat this whole thing as a single anion when you're naming it. So it becomes, and it has a minus charge. Oh, I meant to do the little, right? So this has a minus charge on it. So that means that if you had 1 sodium and one nitrate molecule, you need one of each because this whole thing has a -1 charge. So it becomes sodium nitrate. Cyanide also has a -1 charge on it. So you treat this whole molecule as a single ion. This whole molecule, acetate, has a negative charge on it. You treat this whole thing as a single ion, right? That's why they're called polyatomic ions, because it's not just a single element. These are molecules that are charged. And they work the exact same way that our normal ions do, and you name them just according to their names here. So once we start talking about covalent compounds, it'll be a little confusing because this is a covalent molecule that is charged that bonds ionically to another metal. Because metal or non-metal, most of these are going to be negatively charged. Ammonium is the only positively charged polyatomic ion that we look at. All right, so I just wanted to show you that. If you see it and you don't get it right away, it's okay. We'll talk about it again on Wednesday before you have to turn in the lab. All right, so you guys can go ahead and